It's thinking. Okay, now it's recording. So the homework that I had so much fun grading last night, and sent you all the emails about. Well, so the class average dipped again because the average was nearly 100 for homework 1. It was like 94 for homework 2, and it was like 88 for homework 3. So, interesting trend.
Unfortunate trend.
See? Push.
So hopefully that does not continue. But as a reminder, you do have the opportunity, based on the feedback that I gave you, to fix what you lost points on. And I've had a little bit of taking advantage of that from the last assignment. So be sure to keep that in mind. So there's, I noticed there were some disturbing trends I saw with the code, especially in certain problems. So I'm not going to go over that now because you all can read that in the email. But but efficiency is a very important aspect of these algorithms. So particularly, like if we're storing a matrix in vectors for the banded matrix, so it's not to store it in a two-dimensional array because that wastes storage. Then the whole point is to not go ahead and put all those vectors into a two-dimensional array and just call a \b. So that completely went against the intent of having them in vectors in the first place. So don't do that sort of thing. Those kind of shortcuts will result in hemorrhaging of points. So, also with the only other thing I'll mention was that symmetric positive definite matrices, there are certain criteria that are necessary for a symmetric positive definite matrix to have, like positive determinant, positive diagonal entries. That can be used to rule out a matrix being positive definite. It cannot be used to confirm that it is. So a matrix may have a positive determinant. That alone is not enough. So simply checking that would not be a guarantee. So, but the Cholesky algorithm will succeed without a square root of a negative number or dividing by 0 if and only if it is symmetric positive definite. So a good way to check is based on that. I saw some people also checking like the leading principal submatrices. That works too. That's effective. Okay. Now back to chapter 10. We'll get through most of chapter 10 before good old spring break. That I'm looking forward to just as much as you are. Trust me. And continuing with fixed point iteration. Okay, so I'll do a quick recap of where we were at with that last time, and then we're going to talk about today when to stop fixed point iteration, how many iterations are necessary. Okay, also we established a criterion for convergence. We're going to revisit that because there's a simpler criteria we can use involving a derivative, if it's available. And then give you an idea of when fixed point iteration can go horribly wrong, what it means for a fixed point to be stable or unstable. Okay. And then, last thing I'll talk about is relaxation, or a better title, how I almost invented a root finding method. Unfortunately, I have to say almost.
What was the almost for?
You'll see. Yeah. Okay. All right. Now, so where we're at is one of the simplest iterative method you'll see. Where you're trying to solve the equation f of x equals 0, but you rewrite it in some equivalent form, x equals g of x, using whatever algebraic manipulations you like. Let's see. Okay. And once you do that, you choose your initial guess, x naught. Remember, it's not an exponent. And then you get your new guess by plugging the old one into your function g. And you keep going until convergence. And then we have criterion for existence. G has to be continuous. And it has to map some interval AB into itself. So if it satisfies those criteria, then a solution at least exists. There is a fixed point in AB. And AB, x star is what I keep using to refer to the solution or fixed point. And then uniqueness is that G is Lipschitz. Now, actually, I call it Lipschitz continuous, but a lot of people simply call it Lipschitz because that name is not associated with anything else that I'm aware of anyway, which just means that g of x minus g of y is less than or equal to some constant L, the Lipschitz constant, times x minus y, and we want L to be less than 1, which means that G is called a contraction. So it was actually the last thing I did last time was the contraction mapping theorem, which says that if G is a contraction, it satisfies that condition with L less than 1, then not only is there a fixed point in AB, but it's unique. And fixed point iteration is guaranteed to work. So we're at the same point as we were with bisection. Bisection is guaranteed to work. Find a solution if there's a sign change in the interval. Here we have conditions that also give a guarantee, they're just a little bit harder to meet, unfortunately. Okay, so that's where we left off. We like to. So, as far as stopping criteria, we could just keep performing this iteration and keep checking. Is the difference between two iterates getting closer and closer to 0? Maybe like within some threshold, like xk plus 1 minus xk is less than 10 to the minus 8 in absolute value, something like that. But we like to. But the thing is, just because that difference is getting smaller, it doesn't mean that the error is getting equally small. It's really that error that we want to be small, but we don't know what that is. If we knew, we wouldn't be doing this. So we're going to take a closer look at how do we estimate error in order to determine when we should stop. Okay. Now, all right, so what we know so far is that the error xk, after k iterations, so xk minus x star, because of a Lipschitz condition, that is less than or equal to L times, well, actually, to explain where this comes from. Xk is equal to G of xk minus 1. And x star is G of x star. Bless you.
Thank you.
Now, if I apply the Lipschitz condition, this difference in G values is less than or equal to L times the difference in the x values. Okay. So, in other words, the error bound is multiplied by a factor of L from the old iteration to the new. So, if I keep applying this, that would mean that the error after k iterations is less than or equal to L to the k power times the initial guess minus the solution. Okay. Okay. So the way I get from here to here is I apply this relationship repeatedly. Like this is less than or equal to L squared xk minus 2 minus x star, and so on. So applying it repeatedly gives us this. So we have the latest error is related now to the initial error. The problem is we don't know the initial error either, because we don't know x star, which is what we're trying to get. So here's what we can do. Algebraic triggering. So how do we estimate this? Okay. What we can do is say x naught minus x star. So a lot of error estimation is done using plain old add and subtract trick. So that is x, I'm going to subtract and add x1. Because x1, that's something we do know. Because we take our initial guess, we plug it into G, we get x1. All right, triangle inequality. So I can separate these two terms. Okay. Now this is known. Now this is still unknown because it involves x star. But here's what I can do. I can use this relationship again and say this is less than or equal to, all right, I still have this term. I'll write it underneath. Now this is the error after 1 iterations. That's less than or equal to L times the error after no iterations, so the initial error. Okay. Now, that doesn't seem like I've accomplished very much, except this expression I have the absolute value of is the same as the one on the left side. And L is less than 1. So I'm going to take this, move it to the other side. So then I'm going to have x naught minus x star times 1 minus L is less than or equal to x naught minus x1. And then I can just divide. So now I have a way to estimate the initial error in terms of quantities that I can find out. So the difference between my first two iterates, and then if I can estimate L, if I know something about the derivative, for instance, then I can figure that out. So what I can do now is I can take this and substitute that in here in place of x naught minus x star, because that's just what I've found an upper bound for, and reach my conclusion. And that is the error after k iterations is less than or equal to L to the k over 1 minus L times the difference between my first two iterations. Okay, so this is my error estimate. that I can use in my code. If I have a value for L that's less than 1, so we'll never divide by 0, we don't have to worry about that. Then what I could do is, I want this to be less than some tolerance, like 10 to the minus 8 or whatever. So I can set this less than or equal to that. Also, so I want this to be less than some error tolerance. So I can use this inequality here just algebraically. I can use that to solve for k. In other words, that will tell me how many iterations I need to guarantee that the error will be small enough. Now, I'm not going to solve for k because that's a homework problem, and I'm trying not to do any more homework problems in class. Yeah. But at least that one I remembered. I might do other ones that I don't remember.
This is what you wanted.
What?
I said this is what he wanted.
Okay. Yeah. All right. So any questions about the manipulations here? Now, L has to be less than 1 to be a shorter convergence. But what if L is close to 1? That means that, so this denominator would be small, therefore this whole expression would be large. So if L is close to 1, you'll see when you do a homework problem, that will increase the value of k that's needed to get the error to be small enough. So those kind of fixed point iterations are problematic. They converge more slowly. Okay. Okay. Now, so far, I've described that we want G to be a contraction. It needs to satisfy this Lipschitz continuity condition. But it has nothing to do with a derivative. We haven't even needed a derivative. But if we do have a derivative, then I can state the convergence criterion a little more simply. And they're just begging to drop something. I won't have to buy Teresa a new laptop.
Oh, I can't say that on record.
Okay. All right. So if G is continuously differentiable, on the interval AB, and G prime of x is less than or equal to some constant L, which actually plays the same role as a Lipschitz constant, that's why I'm calling it the same thing, less than 1 on AB, then I can say that G is a contraction. Just as the same way I defined over there. In other words, what I can do is I can say g of x minus g of y. And I'm going to assume that x, y are in the interval AB is less than or equal to, actually it's equal to g prime at some point in between. So C is between x and y. And how do I know this? What theorem tells me this from Calculus 1? Not intermediate.
Just mean value?
It is the mean value theorem.
Yeah.
Oh, you
Okay, got it.
okay. Funny thing is that when Calculus 1 instructors teach the mean value theorem. They give problems involving it that are completely ridiculous. But only at this point, actually, mean value theorem is very important for numerical analysis. A lot of things are proved using it. And then, so here we actually put it to use instead of those dumbass problems they give there. So, like, here you have this relationship. Find the value of C. Who cares? We know it exists. That's what matters. So, whatever. So it's equal to this. And this is less than or equal to L times x minus y, because the derivative is less than or equal to L. So this is the Lipschitz condition. So that's how I'm showing, if this is true, it's a contraction. So if you have a derivative, maybe it's easier to, if you have a formula for derivative, it's easier to check whether this condition is satisfied than the Lipschitz condition itself. So this is just as good as a convergence criterion. I should point out, though, it's not enough. This is not the same as saying absolute value of g prime less than 1. It has to be bounded away from 1. There has to be a gap here. And the reason why is if we don't have that, it's possible that g prime might get arbitrarily close to 1. And that means the error might not actually end up decreasing after all. So that's an important distinction there. Okay. Now, okay, so I'm going to show an example that some interesting behavior you get from fixed points that I got from someone else's textbook. Okay. Suppose g of x is equal to x squared plus 3/16. Okay. So this, if I want to know what fixed points it has, that's where this function is equal to x. Now, without actually bothering to go through it, how would you find the fixed points of that? How would you solve that equation? By hand, I mean.
Quadratic.
Yeah, you can use it's a quadratic equation, so you can use a quadratic formula. And I won't go through all that. The fixed points, there are 2 of them. So there's 1/4
That'd be busy first.
and 3/4. Now, suppose I actually try fixed point iteration on this function to try to get either one of these 6 points. So if I let x naught be equal to, say, 0, or let's suppose I set it equal to or 1/2. Well, actually, yeah. Then what happens is the iterates will converge to the first fixed point, 1/4. Okay. I guess I should try this out in MATLAB, but inconvenient, so I'm just going to tell you what happens. The key is why it happens, and then we'll get to that in a moment. So that's scenario A. Scenario B, I'm going to let x naught be equal to something very close to 3/4. So like instead of 0.75, say 0.74. Actually, I'll get really close. 99999. So you think, oh, well, this should converge to 3/4 because it's right there. Nope. It actually converges to the other one, the 1/4. And then the scenario C, let's suppose I choose x naught to be greater than 3/4, like I said, equal to 1. In that case, there's no convergence at all. It goes to infinity. Dang it.
You ready?
I know. Shut up.
It's not your fault. You didn't put it to sleep.
No, I'm putting the people to sleep.
No.
Okay, so based on the criteria for convergence that I've shown here about the derivative, can anyone tell me why we see this kind of behavior? In terms of this condition. Come on, somebody. Go through a process. What's G prime?
The derivative is 2x.
Yeah. So now the points involved.
1/4 and 3/4.
Yeah.
That'd be a half.
Yeah.
3 over 2.
So.
But 3 over 2 is more than 1.
Yeah.
So it's not.
So the problem is, so G absolute value G prime at the first fixed point is 1/2 less than 1. The other one, G prime 2 star, is equal to 3/2 greater than 1. So this condition for the convergence is not satisfied at the second fixed point. So what we can say is x1 star is a stable fixed point. So if G prime is less than one absolute value at the fixed point itself, we call that fixed point stable. Whereas x2 star, 3/4, is an unstable fixed point. So in other words, if you have an unstable fixed point, you can pick the initial guess as close to that fixed point as you would like, and you will never converge to it, unless you actually happen to get lucky. Like maybe one iteration happens to take you to it exactly. That can happen. But generally, no. You're not going to get actual convergence. So we see it actually wandered away towards the other fixed point. That's how extreme instability is. Okay. So this condition for convergence, G prime being less than or equal to some constant less than 1, that's quite crucial, in fact, to ensure convergence. Now, it's not always a deal breaker, but when it happens at the fixed point itself, when it's violated there, that is a deal breaker. Now, if it's greater than 1, like maybe at certain points near the fixed point, but not the fixed point itself, convergence will tend to be slow, but it can still happen. And in fact, that takes me to the next example, which I did not get from someone else's textbook. It was actually one of my favorite parts of writing this book, because it is something I was playing around with, trying different functions. And this gets to how I almost invented a root-finding method. Time. Okay, I'm doing well on time. Okay. All right, so this was the topic of relaxation, but we won't actually see that until the very end. First, I want to talk about the example. Okay, so this example, I want to solve f of x equals 0. I want to find a root where f of x is equal to x minus cosine x minus 2. And so what I'll do is I'll use fixed point iteration to solve x equals g of x. Or what I'll do is, okay, so I want this to be equal to 0, so I'm just going to move everything else to the other side. So g of x is just cosine x plus 2. So this is my fixed point iteration that I want to have hopefully succeed. So what I need to do is first I need to find an interval AB that has a fixed point. Okay. Because, for instance, suppose, well, I won't go through the whole process of playing around to find an interval that works, but what I need is, for x in the interval AB, I need cosine x plus 2 to be in the same interval. Now, to find an interval that works, I can use the fact that cosine x is bounded by what? Cosine x is between what values?
1 and 1.
Yeah, minus 1 and 1. So, so this expression here is between 1 and 3. Because if I take minus 1 and 1 and add 2 to them, I get 1 and 3. So in fact, since it's bounded by that, I'll use that as my interval. So we use interval 1 and 3. Okay. Now, what I did was, once I picked that interval, I just chose a the initial guess, like x not equal 2. So I'll try fixed point iteration. With my initial guess x naught to be 2, because that's the midpoint of this interval. Okay. Now, I'll draw for you what happened when I did that. Okay, so I have and approximate graph of this function. Okay, cosine 1 is still somewhat positive, so so it behaves something like that. Well, okay, it would really be the graph of cosine shifted up by 2, so I can draw that a little better. Keep that in mind. Okay, so pi over 2 is roughly around here, and pi is roughly around here. Okay, so this graph is really not to scale.
What do you have directly after iteration?
W slash width.
It is a W width. Okay.
Yeah.
I was like LM, don't understand. 4.
Okay, so graph of cosine is supposed to be something like that. Okay. Now, so what happened when I chose the initial guess, x naught right here? Well, I'll also draw y equals x. So right here, roughly, is x star. It's in the neighborhood of pi over 2. So what happens is, what's my g prime?
One minus sine x.
No, g.
G.
Yeah.
Sine
Warmer. Negative sine x. All right. Now, the thing is, that can be as much as 1 in absolute value. So that is indicative of a problem here. So here's what happened. When I actually did fixed point iteration, I got my iterates over here, and then over here, and they kept bouncing back and forth and around the fixed point. And they were approaching a fixed point as I've drawn there, but it was taking a very long time, a great many iterations. Like, well, this is a terrible method. So then I thought, you know, and actually I plotted this exact graph, and it's in the book too, and also plotting g of x equals y equals x, just so I could see where the solution's supposed to be. And what I thought was, you know what? What if I took the average of two consecutive iterations? If they're bouncing back and forth like this, the average is going to be pretty close to the exact value. So here's what I did. So this is roughly equal to -1 near x star, which means slow convergence. Okay. So instead, what I tried, fixed point iteration x equals h of x, and for h of x, what I would use is x plus g of x over 2. So, because whatever iterate this x is, this is the next iterate. So these two will be on opposite sides of a fixed point. You get like here and here. So what I'm doing is I'm taking their average. So, and the thing is, if x and g of x are the same, then this would simplify to x. And I'd have x equals h of x. So solving x equals g of x and solving x equals h of x gives you the same solution. They're equivalent equations. Now, as for why it should be any better, let's look at a derivative. What is a derivative?
Negative 2 times 1, which is 2.
You're not doing a quotient rule, are you?
What?
Please tell me you're not doing a quotient
Of
rule.
course I am. Aren't we dividing h of x? Well, I know it's 0. I know
We're dividing by 2.
minus. Well, nobody else is saying anything out loud, so I mean, don't judge me for.
Hey, can we have something from this side of the room? Not you. Come on.
Is it 1/2 plus g prime of x?
Yeah, or, 1 plus g prime of x over 2. And then g prime we have earlier, that's minus sine x. This is 1 minus sine x over 2. And, okay. Now the thing is, the fixed point is near pi over 2. If a fixed point is near pi over 2, then what is this going to be equal to, roughly? What's sine of pi over 2?
It's 1.
Right? Therefore, this derivative will be roughly... So if x is near pi over 2, 0. Yeah, so this is roughly 0 near x star. So I went ahead and tried this. Converged almost immediately. It was like, wow, shit. So it was so much faster than this because this, my Lipschitz constant, my L, is extremely small. So the error decreased very rapidly from one iteration to the next. So what I was doing, reason why this works so well, is I chose a combination of like x and g of x that it cancels out the slope of g. And so but this worked because g prime was near -1. So by adding x, which has a derivative of 1, you have a near cancellation effect. So since that works so well, I thought, what if I can do this in general? what if I create a fixed point iteration that is like slope canceling in effect? And that's when I thought, maybe I'm onto something, like creating a new method. So here's what I could do. This was a couple years ago. Well, yeah, actually, it was when you were taking a class, Teresa, so I might have mentioned it in that class. But it was 3 years ago.
Yeah, I was like, how long ago was that?
2.5 years ago, yeah.
What's happened since then?
Yeah, a bit, yes. Okay, so this is actually, I gave it a name. Slope canceling fixed point. So what I would do is I would come up with a slope m, like so, an estimate of a slope of g. And I thought, well, I could just use g of xk minus g of
I do remember this. Weren't you?
xk minus 1 over
Pretty sure
xk.
you was up until like 2 or 3 in the morning.
Wait, what?
Weren't you up until like 2 or 3 in the morning trying to do this, and then you realized that it didn't work or something?
Yeah, it was.
Yeah,
Yeah.
I remember this.
Okay. Right. Yeah. And now I'm up till 2 or 3 in the morning trying to prove other things. Okay, but some of them more successful. So then I would solve this equation, x equals h of x, which would be equal to m times x minus g of x, because the derivative of this would be roughly m, and the derivative of this would be m, so they would nearly cancel each other out, divided by, I think I have to make it like this. I'm not sure if that's entirely right, because I have to make sure that if x is equal to g of x, I get, yeah, that is right. Okay. And then, but the thing is, I would change h from one iteration to the next, because this slope estimate would always be changing, but it would be converging to something. And I thought, okay, let's try this out. And I actually started writing a paper, an actual research article about this, where I describe the method and prove how it converges and so forth. And it turns out, because I'm changing h from iteration to iteration, so regular fixed point, so let's talk about order and rate of convergence. So, and I should have mentioned this last time, but no better time than the present. Regular fixed point iteration, the convergence is linear. So in other words, r equals 1. From the quiz that I put out there, I realized that I made a mistake with what I wrote on the board. Order of convergence, I'd said it must be positive, which is true, but it actually must be greater than or equal to 1. So thanks, Timber, for bringing that to my attention. And that's what it says in the book, but what I wrote on the board was wrong. So we have linear convergence, the slowest kind available, and the asymptotic error constant, which I labeled as C, is equal to the absolute value of g prime at the fixed point. And that's why we need it to be less than 1 for convergence to happen. So this is very important, actually. So I'm going to box this. I haven't boxed much today. Because we're going to compare this to other methods that we see. Bisection converges linearly, and the C is equal to 1/2. Here, C is going to be less than 1, but it could be close to 1, or it could be very close to 0. It just depends on G. Okay, so that's the regular method. By contrast, my slope-canceling fixed-point iteration, I get R is equal to 1 again, but I get C converges to 0. Can anyone tell me what kind of convergence that is? I came up on the quiz. What? No, because bisection has a C of 1/2. When C is 0, that's a whole other category. Anybody? What are other kinds of convergence besides linear? Yes, it is superlinear. So I thought, yes, I've created a superlinearly convergent root finding method. And so I'm proving this and so forth. And then I realized, wait a minute, something's wrong here. And I discovered that by rearranging the formula and all that, I actually accidentally reinvented what is known as the Secant Method, which is a method that we'll see later in this chapter, after spring break. And that is a superlinearly convergent method. For R is equal to 1.618, the golden ratio. So, oh well. I should point out this is not the only time that I thought I've invented a root finding method, only discovered that I was reinventing one. But it's fun to do anyway until that crushing blow. Maybe one of these days. But root finding is not my specialty anyway, so yeah. Okay. So that was a fun numerical analysis adventure. Okay. Now, but the thing is, so the takeaway lesson from this, besides make sure that any method you think you've created doesn't already exist, is that we can dramatically speed up convergence if we can get this slope, get G prime, to be as small as possible near the fixed point. And that is useful for guiding selection of G. The smaller we can make the derivative, the more rapid the convergence will be. Okay, so so how to choose G? Again, it's really more of an art than a science, but at least there's some advice to give. I let G of x be equal to x minus lambda f of x, where f is a function we're trying to find a root of. And so lambda is some constant that we need to choose. So we choose lambda to minimize G prime near x star. Now, there's some homework problems that I've assigned that relate to this, so I can only go so far with this. But I want to give the context for you. So I'm going to assume, let's assume that f prime at the root is equal to some value that I'll call m star, so the slope near that point. And I'm going to assume it's positive. Really, what I need is for it to be non-zero, but for concreteness, we'll assume it's positive. Otherwise, we can just work with minus f. And we assume f prime is continuous near x star. So by continuity, that means that as long as we're close enough to x star, f prime is bounded by values I'll call capital M and little m that are positive. Okay. Now, so again, try not to give away too much from the homework.
It's okay.
Now, the thing is, G prime is equal to, just from up here, 1 minus lambda f prime. So what that means is, because of these bounds on f prime, you can get, so from this, you can get upper and lower bounds on g prime. And you want g prime to be less than 1. So for the homework, what you can do is, under these assumptions that I've given, you can choose lambda so that as the value of g prime is less than or equal to L and less than 1, or strictly less than 1, and you can actually find out what L is. And I give a hint in the problem. So I haven't even written up a hints document for this yet, but it's in the problem. It's a very important hint that will help you figure out what L is. So I'm not going to say anything more about that. I've said enough this time. So you can tune lambda in such a way as to make the convergence at least as rapid as possible, given this kind of G. Now, this is a very limiting form of G, but at least it's one that's easy to work with. And also, you can make sure that if you solve x equals g of x, you've definitely solved f of x equals 0, which is the goal here. Now, okay. Now, the thing is, there I'm advocating choosing some value of lambda to use from iteration to iteration. But what if you let g vary from iteration to iteration, which is what I did here? The slope kept changing, therefore my iteration function, my h, kept changing too. If you're able to do that, then convergence can be even faster. So the speed of convergence I can choose lambda to be equal to 1 over f prime at xk. Now, it turns out that this choice of lambda, once you do the homework problem, you'll see why this choice is actually consistent with the one you'll see in the homework. As all the x's get closer and closer to each other. So what that means is lambda is going to converge to 1 over f prime at x star, whatever the root is, which we're assuming is positive. Okay. Now, lambda converges to as k goes to infinity. So let's take this a step further. What if we choose our g of x to be equal to x minus f of x over f prime of x? Which actually, this value of lambda gives us exactly that. So this is equivalent to letting the lambda change from iteration to iteration. Now, let's take a closer look at this g. In particular, the convergence. The asymptotic error constant to c is g prime at x star, an absolute value. So let's take a look at g prime of x star here. So first we need g prime of x. So that would be equal to 1 minus the derivative of this. Now we can use the quotient rule. What would that give us?
F comma of x times f comma of x minus your f of x, f double prime all over f prime x squared.
Okay. All right. Now, let's take a look at let's plug in G prime, let's plug in x equal x star. So G prime at x star is equal to 1 minus f prime at x star squared minus, now x star is the solution. So what happens to this term? F of x star is? It being a root and all?
Zero.
Yes.
Yeah.
We got root finding. So that term is gone over f prime of x star squared. So that becomes 1. So we get 0. So g prime of x star equals 0, which means, given that that's the C, what kind of convergence have we stumbled upon? Superlinear. Yeah. In fact, we can't tell from here, but what can be shown in other ways, which I'll do on Thursday, is so this is superlinear convergence. But if I show this a different way, I can be more specific about the kind of convergence, because if I use Taylor expansion, apologies for any calc-free nightmares that arouses, that if I look at the error, xk plus 1 minus x star, which is g of xk minus g of x star. But now, before I'd use the mean value theorem, now I'm not going to do that. I'm going to use Taylor expansion, and that's going to give me g prime of x star times xk minus x star. Because so this is the center, is x star of my Taylor expansion. Then I'll take it up to the next term. 1/2 g double prime of x star, xk minus x star squared, and then 1/6, I'll just take it up one more term, xk minus x star cubed, and so on. All right, now, so this describes the error after k plus 1 iterations in terms of the error after k iterations. So order of convergence is the relationship between the new error and the old error. Now in the case of linear convergence, the new error is the old error times this factor, the g prime, which is why we need it to be less than 1. So in this situation, g prime of x star is 0, so I cross that out. So what type of convergence do we have now? It's not just superlinear, it's what?
Linear.
No, it would be linear if we had this, but if we don't have this, what's beyond superlinear? Quadratic. Yes. Okay. So yeah, the new error is proportional to the old error squared. So now we have quadratic convergence in this method I've just shown you, where you choose lambda this way. And this 1/2 g double prime in absolute value, that is the C, the asymptotic error constant. Does not have to be less than 1. Now, if this was equal to 0 as well, we'd move to the next term and get cubic convergence and so on. So however many derivatives of g are 0 at the fixed point or at the root, that determines the order of convergence of fixed point. So fixed point is generally linearly convergent, but here we have this special circumstance where g prime of x star happens to be 0, so we hit that sweet spot there, and we have quadratic convergence. Now, what I've just shown you is it is a variant of fixed point iteration, but it's also a very well-known root finding method in its own right. So this method that I've just come up with here is called Newton's method. Okay. So of all the methods we're seeing in this chapter, that is the fastest one. Now I've actually, we're starting to run low on time here. So Newton's method is the main focus of the next section. But there's more than one way to come up with it. You can think of it as a variation of fixed point iteration, or you can derive it a different way, which is what I'll do on Thursday. But I want to show its connection to fixed point. And actually, I think that pretty much concludes my discussion of fixed point, unless I've missed something. I don't think so. Okay. But I've become aware that I seem to cover more than most math classes, so I don't want to keep up my reputation, I guess. Okay. All right. Okay. So, fixed point, as we've seen, it can be a difficult method to apply practically because convergence can fail, as we've seen. Also, choosing G can be difficult. We have some guidelines, like making use of a derivative and so forth, or trying to cancel the slope. Basically, try to make the derivative as small as possible. But that's the overarching theme here. We can make a derivative small, then we get pretty rapid convergence. So it's, on balance, a better method than bisection because it's much more flexible. Even if we come up with fixed point iteration that happens to be slow, we can tweak it to make it faster. And in some cases, like this, much faster. So it's really, it's not just a method in its own right, it's a framework for developing other methods, like Newton's method. It's also very effective for proving that certain equations can be solved at all, because for practical computation, why spend any time solving an equation that you're not sure has a solution? So a fixed point iteration can be used to establish that. And I mentioned this, I might have mentioned it last time, the existence uniqueness theorem for ODEs uses fixed point iteration to prove that a general first order differential equation has a unique solution under certain conditions. Okay, now, since we have a little time left, I want to impress upon you that with the homework grades linearly converging to 0, I don't think they'll get, at this rate they won't get there before the end of the semester, but if you guys are just playing with me and actually this convergence is quadratic and we just haven't seen it yet, then you guys are in trouble. Just a thought, maybe some more questions should be asked before the assignment is turned in. Maybe just a thought. So, if you're not sure what the directions are, what's expected, it's something you can always check with me about. I use your feedback about the problems to improve the statement of a problem, so that when this book is put out there, that students elsewhere will know what to do. And also, I saw a lot of instances where I saw some instances of code being tested, and that's good. But more people need to be doing that. That assignment, I gave some tips on how you can test your code. Like for example, Cholesky. You have your Cholesky function return a Cholesky factor G, and you can check A minus GG transpose. It should be 0 or nearly 0. And several of you, if you had done that, you would have known that your function was wrong. And it actually would have been an easy way to fix it. And now that I was actually doing this last night grading. I ran your code. And not everybody's necessarily, but sometimes I can tell it was wrong just by looking. But just a little bit of rudimentary testing. Run your function and make sure it produces the expected result. So there's a lot of things that can be done that you guys need to be doing so that you can get better homework grades the first time. So it's time to keep that in mind. Okay, well, 5 minutes left, but I'm over it. So I'm sure you all are too.
I do too.